Okay, welcome back. So now we are moved to derive some important equations. The first one is the differential form of the continuity equations. So before that, for the previous slide, we know that what is the continuity equations. The continuity equations is follow the mass in CV volumes dmCV dt plus the mass flow rate out minus the mass flow rate in is equal to 0. Okay, and usually we call that there is this is the mass conservations. But right now we move to the different systems. The systems we focus on a small particle, qubit. And if you take a look for a small qubit fluid particles, so in here we have the Y, we have the X, and we have the Z. So three-dimensional coordinate. And first we focus on the control volume and the control surface on the Z-X plane. Okay, so we have this is for the Z-X plane, and we have the flow directions is along the X directions. So we have the U velocities, okay, along the X directions. So if we consider this is the point for the in, and this is the point for the out, and we define our control volumes, and the rotation line is the control surface, and at the 0 point for the centers, the physical property is the density multiplied the U flow velocity. And can we predict the density multiply the velocity values at the out point, and the density multiply the velocity at the point in? So we base on the Taylor's expansions. We know that the location difference from 0 from the center to the out here is the delta x divided 2, and then there is also the delta x divided 2. Because the Taylor expansions tell us if we know that the point, we know the values at the point 0 center is the rho u, and in that the point here we can predict the rho u in that right hand side point is plus the d rho u dx multiplied 2 over delta x. And the Taylor expansions also have some high order items, like we will have the second differential rho u and rho x squared multiplied the delta x divided 2 squared, and so on. But we assume the delta x is quite smaller in here, so the square item and some higher order item is equal to close to 0. So in that way, we only have the the first differential items. That means we assume the low U physical parameters will be changed along the x direction is linear. That means the gradient of the low U along the x is constant values. Okay, so similarly, we can predict the pressure. We can predict the low U values in the left-hand side. So this is a low U, but we need to have the minus. Why we use the minus in here? Because the delta x over 2, the 2 over delta x is the minus to the left hand side. Okay, so we know that we have the right hand side low U values and the left hand side low U values. So we can go back to the continuity equations. There are some net of the outflow. So we need to have the outflow mass rate minus the inflow mass rate. Since we know the low U value on the right hand side, the right hand side is outflow. So we have the low U values is the low U plus the D low U dx. The gradient is constant, follow a linear increase along the x, and multiply the delta x divided 2. We know the low U multiply the areas is equal to the mass flow. So along the xz plane, the area is the dy dz. Okay, because we consider the domain of the plane is along the x and the z directions. So the area curves on the right hand side curves papers inside is delta y multiplied delta z. Okay, so we can this is our mass flow for out. So again, the inflow mass rate can be right as the low U minus the d low U dx delta x divided 2, and also we have the same cross-section areas dy dz. Okay, so if you put two equations inside to the net outflow mass rate, and then you have a low U plus the low U dx multiply 2 over delta x and multiply delta y delta z minus the low U minus the low U dx 2 over delta x multiply the cross-section areas. So you can cancel out the low U and the low U. And the 2 over x, the low U dx minus minus, so become the plus. So you can know that the net outflow mass rate along the x directions is the low U dx multiply the delta x delta y delta z. So if you follow the previous equations derivation, and then you focus on the net outflow rate, mass rate along the y directions. So if along the y directions, that means we are focused on the xy plane. And you also can compute the net outflow mass rate along the z directions. Okay, and in that way, we are focused on the YZ plane. Okay, so here we know that the answer may be similar to the x directions. So there is a d rho v d y delta x delta y and delta z. And this is for the z directions. So there is a d rho w and the dz. Also multiply delta x, delta y, and delta z. And if you summarize the total outflow mass rate is equal to the mass rate along the x plus the mass rate along the y and plus the mass rate along the z directions. So this is equal to the rho u dx plus the rho v dy plus the rho w dz and multiply the delta x, delta y, and delta z. Okay, so if we look at these items, it's similar. We can rewrite to a divergence as a divergent items. So this is equal to the gradients and the dot product, the rho v vectors, and multiply the delta x, delta y, and delta z. Okay, so this is for the final net outflow mass rate. And then we go back to process. Another item is the mass in the control volume change with the time. As we know, the MCV in here, we have the density, and we know the qubit body volumes is delta x, delta y, delta z. So we can put the MCV back to the continuity equations. So there is the MCV, the MCV dt, and the right hand side here is the total mass flow rate and equal to 0. So here we can easily to cancel out the total volumes of the qubit. Okay, so the first item we only have a density change with the time, and there is the divergence of the density multiplied the velocity field. So this is a dot product in the rho v vectors. Okay, so this is our final journal formula for the continuity equations in the differential form. So if we consider the continuity in the differential form is satisfy the steady flow conditions. We call that what is the steady flow. The steady flow, that means the physical property didn't change with the time. So for this continuity equation, we only have the first item related to the time point. So for the steady flow, we don't have these items. So this is the formula equal to 0 for the steady flow. But if we consider The flow is incompressible flow, so that means the density didn't change with the space. So that means if we consider the differential rho u and rho x, you can rewrite the differential to be the rho dx multiply u plus the rho du dx. If we consider the flow is incompressible flow, so the density didn't change with the spatial changes. So finally we can take the density outside and equal to du dx. Okay, so this is the equation only satisfied when the flow is the incompressible flow. And also, we know that if the density doesn't change with the spatial, also satisfy the density doesn't change with the time. So in that way, we don't have these items, and the law can take outside, and then finally we have the divergence of the velocity field is equal to 0. So this is divergence of the velocity field equals to 0 only satisfied when the flow condition is compressible flow. So as you remember, I tell you the curl operators of the velocity field is equal to 0. That means I can tell you the flow is rotational flow, right? And but now we have the new ideas for the divergence of the velocity field. So this is very useful to describe the velocity field. As you can see the figure showing here, this is the wall fixed on the right hand side, and you have one fluid particle on the left and try to flow forward to the wall. And this is the u, and this is the v velocities. So in this direction is x, in this direction is the y. And if you take a look, this is a two-dimensional velocity field, and this is along the xy planes. So we can rewrite the conversion of the divergence of the velocity field to become the dv dx minus du dy. Okay, sorry, I rewrite this. The divergence is du dx plus dv dy. This is the two-dimensional for the divergence of the velocity field is equal to 0. So you 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 see that the u velocities change with the x increase for this problem is minus, because the x increase, the u arrow showing here becomes smaller. Okay, so the gradient of the u velocity along the x direction is the minus. But if we look the v velocity along the y directions, it's from the small and the increase a lot on the right hand side. So for this value is positive. And then finally they need to balance each other and equal to 0. So we know the divergence operators of the velocity field can tell us and can describe the velocity field. So this is very useful to describe the velocity field. The velocity field need to satisfy the divergence theorem in here. Okay, and the curl operator can tell us the flow is rotational or not. Okay, so how to apply the divergence of the velocity field? So the question already tell you this is a 2D incompressible and steady flow, and we know that the flow functions along the x directions is the u equal to minus x divided y and multiply the capital U. And this is the boundary conditions. And what is the y direction velocity? Okay, so based on these assumptions, the flow is satisfying the divergence of the velocity field is equal to 0. And because this problem is based on the 2D flow, so we know that the du dx plus dv dy is equal to 0, right? And then we only have the u functions in here, so there is the dx, and then we put the u function. The u function is minus s y capital U, and plus the dv dy and equal to 0. Okay, so the function is differential with the x, so there is minus u over y over capital U plus dv dy equal 0. And then we move to the item to the right hand side to become a u and divided by y. Okay, and then the e is equal to u divided y dy, and with both sides we do the integrations. Okay, so the left hand side is the v equal to the right hand side is the u known y plus the c. Okay, so but in that right now we don't know the constant value in here, but we have the boundary condition tell us that v x y equal 1 is equal to 0 velocity. So we put the y equal 1 inside the equation. There is the 0, and will be the 0 equal to 0. So that means the c is also equal to 0. So finally, we know that the u ln y is our v velocity. Okay, so we just check the flow condition is incompressible flow, and then we can follow the divergence of the velocity field equations to predict the velocity functions. Okay, so this is very common in the fluid mechanism problems. So usually we use the divergence of the velocity fields try to describe the velocity functions u or v. Okay, so And the following slide, I would like to introduce the two functions. The first function is we call that the string function, and usually we use the perceive symbols in here, and you can take a look the sentence showing here. The string functions are defined for a 2D flow and for a 3D symmetric flow. The string function can be used to plot the string lines of the flow and find the velocity. So for the 2D flow, the velocity components can be calculated in Cartesian coordinates by the equation shown here. So this is very important that u is equal to d perceive dy minus and the velocity v along the y directions is equal to d perceive dx. So please remember the definitions of the string functions with the relationship have a relationship with the velocity. So the idea is for this definition is the string functions gradient along the y directions is equal to the u velocity. And the string functions have the gradient with the x direction is equal to the velocities for the y directions. And based on this equation, and we also assume the flow is irrotational flow. In the irrotational flow, we know the operators for the velocity field is equal to 0. So this is we focus on the two-dimensional planes. So we know that we can rewrite the code of the velocity field to be the dv dx minus du dy and equal to 0. And you put the v is the perceive dx inside here, and the u is the perceive dy minus in here. Finally, you can have the result like the formula showing here. And we call that this is a Laplace equation for the string function perceived if the flow is satisfied rotational. Okay, so this is very important definitions. Please remember. And the string functions, the contour of the string function can depict the string line of the flow. So that means you know the perceived functions in your flow conditions, and then you can draw the string lines of the flow. Okay, and what is the potential functions? We use the phi operators. So, and the potential function can be defined by the u is equal to dy dx, and the v is equal to d phi dy. And if we remember, we have a continuity equation in differential form for incompressible flow. So we know that the divergence of the velocity field is equal to 0. And so we can rewrite the divergence of the velocity field for the 2D problems. So du dx plus dv dy is equal to 0. And you put the u is the du d phi dx inside here, and the v is d phi dy here, and you can also have a Laplace equation for the potential functions of the phi. And the right hand side just for the cartoon figure showing the blue line is the perceived is the string functions. And if a string function is equal to constant, you can define the contour of the string lines. So the string functions of the contours is equal to the string lines. So the blue line in here is string lines, and the red line in here, we call that the potential function. So you can see clearly the potential functions line is always perpendicular to the string lines functions. Okay, so the perceived and the phi, one is the string functions and another is the potential functions. Usually can be used to describe the velocity flow velocity, and the string function is related to the string line, and the potential function is the line perpendicular to the string line. So this is a very important two parameters to describe the flow. So we put the one exercise in here, and this is we focus on curvature flow, and we describe the curvature flow in the chapter 2. In that topic, we are focused on the viscosity effect, and we also tell you the curvature flow. The topic is related to the rotational flow. So actually, the curvature flow is a rotational flow. So we need to take a care of the viscosity effect. So as you see, the curvature flow is a flow that is driven by a moving wall with a velocity u here. And the velocity profile in the fluid is linear. Okay? And it can be defined as the u-y function is equal to the capital U multiply y divided L. The L is the thickness of the curvature flow. So the simple questions in here is, what is the string functions? What is the string functions? The string function is perceived of the curvature flow. Okay, and we assume this is a string line directions, and we use the x directions also. The string line directions is parallel to the x directions. Okay, so as we know the certain definition of the string functions, the u is equal to the minus the perceived dy. Okay, and we also know that the v velocity the perceived dx. Okay, so because we focus on the two-dimensional curvature flow, so we only need to take a look for the u velocity and the v velocity. So in the curvature flow, we exactly know that we don't have the velocity along the y directions. So the v is equal to 0. So we know that the perceived dx is always equal to 0. right? So that means the perceived functions is equal to, if we process the integrations, is equal to the gy functions. Because if the perceived functions only have the y functions, and we have the differential cases, so the result is equal to 0. Then maybe we have an additional constant value, right? And we also know that u functions is equal to the capital U multiply the y divided L. Okay, and the following is the definition of the string function here. So we know that the u y L is equal to the minus the perceived dy. Okay, and we just move the dy item to the left hand side. So there is a u divided L y dy, and there is the minus also. And the right hand side we only have a d per c, and we process with the integrations both sides. So we know that the perceived functions is equal to the minus u L 2 over y squared. Okay, so actually you can compare. This is the equation 1, and this is the equation 2. If you compare the equation 1 and the equation 2, you will know that the perceived functions, this is only have the perceived function only as a function of the y, and this equation 1 tells us the perceived function should be related to the y function only. Maybe additional constant we will have. Okay, so based on the 1 and the 2, we can conclude that the perceived function is only a function of the y. So we have the minus and the y squared plus divided 2, and also we have the additional constant values. And then we assume the perceived functions on the bottoms. The perceived function on the bottoms, this is equal to 0. So what are the coordinates on the bottoms? We know that the perceived on the bottoms, the y is always equal to 0. So we put the y inside these equations, and the plus the constant value is equal to 0. Okay, we assume the bottom is the perceived 0 is equal to 0. Okay, so we know that the constant is 0. Okay, so how about the perceived function in the middle part? So the middle part, we may call that is the perceived one. So in the middle part, we know that the y distance is half of the L. Okay, so y is 2 over L. So what is the perceived one? The perceived one is equal to the minus u divided L and the 2 over 1 and the y squared. Y is 2 over L, so the y squared is 4 over L squared. So this is, you can cancel out the L, and we only have the minus UL divided the 8. And maybe we can continue to calculate the string function on the top. We call that is the C2. So in that way, the y function is the L. The y length is the L. The C2, we put the y equal to L inside the equation here. So it's equal to the UL divided 2. Okay? And that means we previous slide we tell you the contour of the string function are the string lines. As you can see for our questions, I depict the string line for the C0, C1, and the C2. They are parallel to the x directions. Because the C functions didn't change with the x increase, but will be changed when at the different y values. Okay, and you see the difference is the C1 from the y from 0 to y equal to 2 over L. The perceived functions, the C1 to the perceived 0 is the minus UL divided 8. But if the same delta y changes, but you can see the different perceived function difference. The y is 2 over L, but move to the y equal L. There is the perceived function 2 minus the perceived function 1. So the perceived function 2 is the minus UL divided 2 plus 8 over UL is equal to the minus 8 and the 3 UL. So that means the gradient delta per c divided the y changes. The gradient in here is large than the gradient in here. So the string line on the top will curve much curves, but the string line between the y1, the per c1 and the per c0 will large. Okay. So this is our final result. We can define it. Follow these equations plus the string function. We can describe the string line at the different y locations. Okay, so that's why I tell you the string functions can tell us the string line of the flow. And for this exercise, our flow is not irrotational flow. If our flow satisfies the irrotational flow, we can also apply the Laplace equation for the string line and try to try to understand the velocity field under our flow condition. Okay, so this is our final exercise in these chapters. 好，那这是我们今天的最后一个 slide。那我来稍微说明一下，就是下周一我们可能的这个考试的这个内容。那第一个，下周一一定会考的是如何去运用我们的连续方程跟伯努利方程。那如同这个案例里面告诉我们，连续方程我们有 Q1、Q2， 或者是说我们可以说 A1、E1 等于 A2、B2。那这样子的关系，可以写成这样的关系。第一个是 uniform 的 flow， 那第二个是不可压缩流，所以我们的 rho 永远都是 constant， 那你就可以写成这样子。因为 Q1、Q2 本来是来自于质量流率的这个 balance。OK， 那第二个是我们一定要知道伯努利方程，因为伯努利方程可以告诉我们 pressure 高层的 pressure 加上速度的导致的 pressure， 那在同一条 string line 上，它一定要满足这样的关系式。所以你有连续方程，你有伯努利方程，你可以去任意的去知道 pressure， 或是任意知道在不同位置的 velocity。有两个关系式，你就可以去求解这些未知数。这在我们在应用流体力学上面这一部分是非常重要的，所以下周一定会再考一题有关于连续方程跟伯努利方程的另外一种应用的这个方式这样子。那另外一个对大家在课本教材里面相对找不到的内容，就是从第53页开始。我们有连续方程的微分形式。那只是把之前的这种连续方程的表示式，透过一个比较小的fluid 的这个 particle 来做这个分析。那在分析的过程中，我们可以知道可以满足这个就是 general 的这个微分形式的连续方程，但是我们有两个条件，一个是 steady flow， 我们就可以把微分方程形式连续方程的微分形式写成简化成low v 的这个 Divergence。那如果我们又假设这个流况是不可压缩流，那其实就主要就是速度场的 Divergence 会等于0，然后用来描述这个速度场。那因为这个样子，所以我们又跟你说，其实有两个函数，一个叫做流线函数 string function perceive， 那它定义方式写在这个地方。这个很重要，大家一定要记得。那另外一个，所以我们知道可以用流线函数来描述流场的流线。那某个条件下也可以进一步了解流速的状况。那另外一个方程是 phi， 那我们说是四流函数。那其实这个函数它会定义出来的方程会垂直于这个流线的这个方向。那所以我本堂课可能大家记得一个就好，就是 string function， 这个 perceive 的符号。那我们下周一定也会考一题这个 string function。OK， 那提醒各位在下周记得在上传作业，那拍摄图档，那这个照片解析度可能要高一点。那以后我们如果 没有意外的话，就是会在考试后批改完各位缴交的这个考试卷，那就会将最后的成绩上传到1、3的平台，那也一并会在上传成绩的之后也提供考试的详解，让各位同学可以回去思考一下自己写的答案跟详解里面有什么样的这个出入，那为什么助教会给你这样子的分数？那如果你对于分数有问题的，也欢迎来我们工二馆的420的学生研究室，那去询问一下助教为什么给你这样的分数。那为了防疫期间这个安全的重要性，所以大家一定要事前跟助教约时间，那保持室内空间不可以超过5个人。那像有同学跟我约询问一些问题，我也都很乐意，所以也会回信跟你呃提供一些什么时候是适合讨论跟问问题的时间。好，那以上谢谢。那我们下个礼拜一，希望各位同学可以在考试这部分更加顺利。OK。